Welcome to this problem-solving session. Today, we'll tackle an interesting problem called kth smallest prime fraction. This challenge will test your understanding of algorithms and problem-solving strategies. Let's dive in. In this problem, we are given a sorted array of unique integers called ARR. These integers are prime numbers, and the array is sorted in increasing order. Our task is to find the kth smallest fraction that can be formed by dividing two elements of this array. Specifically, a fraction is formed as ARR I/ARR j, where I is less than j. For example, if ARR is 2, 3, 5, possible fractions would include 2/3 and 3/5. The fractions must be considered in ascending order of their numerical values. Ultimately, the solution should return the kth smallest fraction as a list containing two integers, the numerator and the denominator. The input includes the array ARR and the integer k, where both have specific constraints. The output is a list, numerator, denominator, representing the desired fraction. Let's explore an example to clarify the problem. Suppose the input array is ARR equals 1, 2, 3, 5, and k equals 3. This means we need to find the third smallest fraction that can be formed using the elements of ARR. First, we generate all possible fractions, 1/2, 1/3, 1/5, and so on. These fractions are calculated by taking one element as the numerator and a later element as the denominator, ensuring I less than j. To determine which is the third smallest, we need to sort these fractions by their values in ascending order. This process will help us identify the correct fraction to return. Continuing with the example, the complete list of fractions from ARR equals 1, 2, 3, 5 would be 1/2, 1/3, 1/5, 2/3, 2/5, and 3/5. Calculating their decimal values, we get 1/5 equals 0.2, 1/3 equals 0.333, 2/5 equals 0.4, 1/2 equals 0.5, 3/5 equals 0.6, and 2/3 equals 0.666. Sorting these fractions by their values gives the order 1/5, 1/3, 2/5, 1/2, 3/5, and 2/3. In this sorted list, the third smallest fraction is 2/5, which corresponds to the output 2, 5. This demonstrates how we identify the desired fraction after sorting. Now, let's look at another example where ARR equals 1, 7, and k equals 1. Here, there is only one fraction possible, 1/7. Since there are no other fractions, and k equals 1, the first smallest fraction is simply 1/7. Hence, the output is 1, 7. This example highlights that in cases with very small arrays, the solution must still handle the inputs correctly and return the only available fraction. Let's consider another example with a larger array to see how multiple fractions are compared and sorted. For the input ARR equals 1, 2, 3, 5, 7, and k equals 5, we first calculate all possible fractions. These include 1/2, 1/3, 1/5, 1/7, 2/3, 2/5, 2/7, 3/5, 3/7, and 5/7. By evaluating their decimal values, we can sort them in ascending order: 1/7, 1/5, 2/7, 1/3, 3/7, 2/5, 1/2, 3/5, 2/3, and 5/7. The fifth smallest fraction in this sorted list is 3/7. Thus, the output for this input is 3, 7. This demonstrates how the solution handles cases with larger arrays by systematically sorting and selecting the desired fraction. Finally, let's discuss some important constraints and edge cases. First, all fractions will have unique values because the integers in ARR are unique prime numbers. For edge cases, if the array contains only two elements, such as ARR equals 2, 3, there will be only one fraction, and the solution must handle this minimal input correctly. For larger arrays, such as when ARR contains up to 200 prime numbers, the solution needs to efficiently handle up to 19,900 fractions. Additionally, when the prime numbers in ARR are close to 10^4, the solution must ensure that numerical precision is maintained when comparing fractional values. Lastly, when k is the largest possible value, meaning we need the largest fraction, the solution must still produce accurate results. These considerations ensure robustness across all input scenarios. To start, let's consider the brute force approach. The intuition here is fairly straightforward. Since the array ARR contains unique primes sorted in increasing order, we can generate all possible fractions of the form I/arrj, where I is less than j. Once we have this list of fractions, we can sort them and locate the kth smallest fraction directly. However, while simple to understand, the brute force approach comes with significant drawbacks. Computing all fractions results in O, n squared, combinations, and sorting them adds an additional O, n squared asterisk log, n squared, time complexity. Not only does this approach require a lot of time for larger arrays, say when n greater than 10⁻3, but it also demands substantial memory to store the fractions. As a result, while effective for small inputs, this method becomes computationally expensive and impractical for larger problem sizes. An optimized approach involves using binary search on the values of the fractions instead of explicitly generating and sorting them. The key idea is to leverage the fact that the array ARR is sorted, which allows us to treat the problem as finding the kth smallest element in a conceptual sorted list of fractions. Here's how this works. We define a range of possible fraction values, starting with low equals 0.0 and high equals 1.0. For a midpoint value, mid, we count how many fractions in ARR are less than or equal to mid using the sorted order of the array. During this process, we also keep track of the largest fraction that is still less than or equal to mid. Based on the count, we adjust our binary search range until we zero in on the exact kth smallest fraction. This approach is significantly more efficient, with a time complexity of O, n asterisk log, max underscore denominator, where max underscore denominator refers to the largest denominator in the fractions. It also uses constant additional space. While the logic for binary search may be slightly more complex to implement compared to brute force, the efficiency gains in both time and space make it a compelling choice. Another optimized approach makes use of a min heap to efficiently track and extract the smallest fractions. The idea here is to start with the smallest fractions, which are those with RR, 0, as the numerator, and iteratively extract the smallest fraction from the heap. For each fraction that is removed, the next fraction in the sequence is added to the heap. Specifically, we initialize the heap with the fractions ARR, 0/ARR, j, for all j greater than 0. Then, we perform k extractions, and during each extraction, we push the next fraction in the same row into the heap. After k extractions, the kth smallest fraction will be the last one removed from the heap. This method is efficient with a time complexity of O, k asterisk log, n, where k is the number of extractions and n is the size of ARR. It also uses O, n, space for the heap. Although this approach is straightforward to implement and efficient, it requires additional memory for the heap and can become slower when k is large due to repeated heap operations. Ultimately, while effective, it is not as optimal as the binary search approach. There are a few key insights that make the binary search approach particularly powerful. First, the sorted order of ARR ensures that when we traverse fractions row by row, they are also non-decreasing. Second, rather than explicitly constructing all fractions, binary search on the values of the fractions allows us to narrow the search space efficiently. Third, counting how many fractions are less than or equal to a given mid can be done efficiently using a two-pointer technique, which again leverages the sorted nature of ARR. These observations lead to the aha moment. By combining binary search with the sorted properties of ARR, we can solve the problem in a highly efficient and scalable manner. That said, every approach involves trade-offs. While binary search requires careful implementation, it is the most efficient in terms of time and space. The min-heap approach is simpler but less optimal for large k values due to the additional memory overhead. Meanwhile, the brute force method, while conceptually easy to grasp, is not practical for larger inputs due to its high computational cost. By focusing on binary search, we achieve the best balance of efficiency and scalability, making it the ideal strategy for solving this problem. To solve the kth smallest prime fraction problem, we start by understanding its requirements. Given an array of unique prime numbers sorted in ascending order, we need to find the kth smallest fraction of the form ARR, I, divided by ARR, j, where I is less than j. One straightforward way to approach this is through a brute force method. First, we generate all possible fractions by iterating over every pair of indices I and j, ensuring I is less than j. For each valid pair, we compute the fraction ARR, I, divided by ARR, j, and store it as a tuple containing the numerator and denominator. Once we have all these fractions, we sort them in ascending order based on their floating point values. Finally, since the fractions are now sorted, we can directly access the k1th element in the zero-based index and return it as the result. While simple to implement, this approach has significant computational overhead, as we'll see next. Now let's analyze the brute force solution further. One key insight is that because the array consists of prime numbers, each generated fraction is automatically in its simplest form. This eliminates the need for additional steps like reducing fractions. However, sorting all the generated fractions is computationally expensive. Specifically, generating the fractions involves n² time complexity since we compute all possible pairs of I and j. Sorting these fractions, given their count of n², requires n² log n² time. Combined, this makes the brute force approach inefficient for large arrays. The data structure we primarily rely on here is a list of tuples to store fractions as numerator-denominator pairs. This structure facilitates easy sorting and retrieval. The core operations include fraction generation for all valid pairs, sorting the list using Python's timsort algorithm, and accessing the kth fraction in constant time. While functional, this method's inefficiency highlights the need for more optimized solutions. To address the inefficiencies of the brute force approach, we can explore optimized methods. One such alternative is the heap-based approach, which leverages a priority queue to efficiently find the kth smallest fraction. This method avoids generating and sorting all fractions, achieving a time complexity of k** log n. Another optimization involves using binary search combined with a two-pointer technique. Here, we narrow down the range of values for the kth smallest fraction through binary search, while two pointers help count fractions below a given threshold. These optimizations drastically reduce the computational load. In terms of complexity, the brute force method still requires n² log n² time and n² space, making it unsuitable for large arrays. Edge cases further emphasize the need for efficiency. For instance, when k equals 1, the smallest fraction is trivially ARR 0 divided by ARR-1. For large k, close to the total number of fractions, the brute force method remains inefficient. Tiny arrays, such as those with only 2 elements, are trivial to handle, but for large arrays, the brute force approach quickly becomes infeasible, underscoring the necessity of adopting these optimized methods. This Python solution efficiently determines the kth smallest prime fraction using a min-heap priority queue. Here's how the code works. 1. Initialization. The kth smallest prime fraction function takes a sorted list of unique prime numbers, ARR, and an integer k. We aim to find the kth smallest fraction of the form ARR i/ARR j, where I less than j. 2. Min-heap setup. A min-heap is used to maintain the smallest fractions. Initially, the heap is populated with fractions of the form ARR i/ARR-1, the smallest prime divided by the largest, for all valid numerators. Each heap entry is a tuple, fraction_value, numerator_index, denominator_index, where fraction_value is the evaluated fraction value. 3. Heap extraction. The algorithm extracts the smallest fraction from the heap, k times. The heap structure ensures that we always access the smallest fraction efficiently. For fraction update, after popping the smallest fraction, ARR i/ARR j, if the denominator index can be reduced, i.e. j greater than I plus 1, the next fraction, ARR i/ARR j1, is pushed into the heap. This ensures we explore fractions in sorted order. 5. Result construction. After k extractions, the required kth smallest fraction is found. The function returns the fraction as numerator, denominator. Efficiency. This method optimizes the search by only maintaining the smallest fractions in the heap, avoiding the need to generate and sort all possible fractions explicitly. The time complexity is approximately k log n, where n is the length of the array, making it highly efficient for this problem. Edge cases. The algorithm handles edge cases such as small arrays, e.g., RR of size 2, and ensures the fractions are correctly ordered without duplicates since all elements in ARR are unique primes. Here, we start by importing the necessary libraries and defining our solution class. The main method we're working with is kth smallest prime fraction, which takes an array of integers ARR and an integer k as inputs. To solve the problem, we use a min-heap, implemented with a priority queue, to efficiently track the smallest fractions. The priority queue is configured to compare fractions based on their values, calculated as the division of two array elements. Next, we initialize the heap by iterating through all elements of the array except the last one. For each element, we push an initial fraction into the heap, where the numerator is the current element, and the denominator is the last element of the array. This ensures that all our fractions start with the smallest possible denominators, which helps maintain the priority order. After this initialization, we'll move on to extracting the smallest fractions until we find the kth smallest. Now, we extract the smallest fractions from the heap exactly k times. Each time, we pull the heap to retrieve the fraction with the smallest value, storing its numerator and denominator in the result array. The indices corresponding to this fraction are tracked as I for the numerator and j for the denominator. Once we retrieve the smallest fraction, we check if there's still another valid fraction that uses the same numerator but a smaller denominator. If such a fraction exists, we push it into the heap to ensure it's considered in the subsequent iterations. After k iterations, the result array will contain the numerator and denominator of the kth smallest fraction, which we return as the output of the function. This approach ensures efficiency by leveraging the properties of the min heap to always focus on the smallest fractions at each step. To solve this problem, we aim to find the kth smallest fraction that can be formed using an array of sorted prime numbers. Each fraction is derived from two distinct indices I and j in the array, where I is less than j. To efficiently track and retrieve the smallest fractions, we use a min-heap data structure. For example, given the array 1, 2, 3, 5, and k equals 3, we start by initializing the min-heap. The first step is to push fractions into the heap, using the last element of the array as the denominator for each fraction. Specifically, we push 1/5, represented as 0.203, 2/5, as 0.413, and 3/5, as 0.623. After this step, the heap contains these fractions in ascending order of their values. The next step is to extract the smallest fraction from the heap k times. With each extraction, we pop the smallest fraction and push a new fraction from the same numerator, but with the next smaller denominator. For the first extraction, we pop the smallest fraction, 0.203, corresponding to 1/5, and push a new fraction, 1/3, represented as 0.33302. After this operation, the heap updates to include the new fraction. For the second extraction, we pop 0.33302, or 1/3, and push 1/2, as 0.501. Finally, for the third extraction, we pop 0.413, or 2/5, and push 2/3, as 0.66612. At this point, we have extracted the third smallest fraction, which is 2, 5. Now, let's consider another example with the array 1, 7, 23, 29, 47, and k equals 4. As before, we initialize the min heap by pushing fractions where the last element, 47, serves as the denominator. Specifically, we push fractions 1/47, 7/47, 23/47, and 29/47 into the heap. These correspond to the entries 0.0210, 4, 0.148, 4, 0.489, 4, and 0.617, 4 in the heap. Next, we perform k extractions. In the first extraction, we pop 0.0210, 4, or 1/47, and push 1/29, as 0.03403. In the second extraction, we pop 0.03403, or 1/29, and push 1/23, as 0.04302. For the third extraction, we pop 0.04302, or 1/23, and push 1/7, as 0.14301. Finally, for the fourth extraction, we pop 0.14301, or 1/7. Since no additional fractions can be formed with 1 as the numerator, we stop here. The result of this process for the given example is the fourth smallest fraction, 1, 7. Now, consider another example with the array 2, 3, 5, 7, 11, and k equals 6. We initialize the heap by pushing fractions with 11 as the denominator, 2 11ths, 3 11ths, 5 11ths, and 7 11ths. The extraction process proceeds as follows. First, we pop 2/11, then 3/11, followed by 5/11, and 7/11. At this point, we begin pushing fractions with the next smaller denominators. We proceed to extract 2/7, and finally 3/7. After 6 extractions, the sixth smallest fraction is 3/7. The key to this solution lies in the efficiency of the min heap. The heap allows us to dynamically track and extract the smallest fractions while maintaining the sorted order. By pushing fractions with decreasing denominators, we ensure that the next smallest fraction is always available at the top of the heap. With a time complexity of O, n log k, where n is the size of the array and k is the number of extractions, this approach is both efficient and straightforward. By leveraging the properties of the heap, we achieve a balance between computational efficiency and clarity in implementation. To analyze the time complexity of our solution, let's break it down step by step. First, we initialize a min heap with fractions of the form arr_i/arr-1, where I ranges from 0 to n2. Since there are n1 fractions initially, and each insertion into the heap takes O log n time, the total time complexity for this initialization step is O n1 asterisk log n, which simplifies to O n asterisk log n. Next, we perform heap operations over k iterations. For each iteration, we pop the smallest fraction from the heap, which takes O log n, and if possible, we push the next fraction with the same numerator but a smaller denominator, also taking O log n. This involves up to 2 heap operations per iteration, resulting in a total time of O k asterisk log n for k iterations. Together, the heap initialization and the heap operations give us the overall time complexity of O n asterisk log n plus k asterisk log n. Now, let's summarize the overall time complexity. Since k is typically much smaller than n-2, the total number of fractions we could generate, the dominant term is O n asterisk log n. Therefore, the time complexity of the solution is O n asterisk log n. Moving on to space complexity, the heap plays the biggest role. At most, the heap holds n1 elements, where each element consists of a fraction value and 2 integer indices. This gives a space complexity of O n for the heap. Additionally, the algorithm uses a few auxiliary variables, such as those for the current fraction and its indices, which require constant space, O1. When we combine these, the total space complexity is dominated by the heap, resulting in O n. Finally, let's compare this heap-based approach to the brute force method. A naive solution would compute all possible fractions arr/j for 0 equals I less than j less than n, sort them, and return the kth smallest fraction. Generating all fractions has a time complexity of O n squared, and sorting them adds an additional O n squared asterisk log n squared, simplifying to O n squared asterisk log n. The space complexity is also O n squared, since all fractions need to be stored. In contrast, our optimized approach only processes necessary fractions using a heap, reducing the time complexity to O n asterisk log n, and space complexity to O n. This makes the heap-based solution far more efficient, particularly for large arrays, as it avoids the overhead of generating and sorting all possible fractions. Overall, this optimization ensures that both time and space usage are kept to a minimum while maintaining accuracy. When solving this problem, there are several common mistakes to watch out for. First, forgetting the constraint that I must be less than j when generating fractions can lead to duplicates or invalid results. For instance, if you generate both arr/j and arj/ri, you're not only wasting computation but also violating the problem's constraints. To fix this, make sure you enforce the condition I less than j when creating fractions. Another issue is attempting to sort all possible fractions naively. This approach has a time complexity of O n squared asterisk log n squared due to the large number of fractions generated, which quickly becomes impractical for large arrays. Instead, optimized strategies like binary search or using a priority queue can help you avoid this inefficiency. Additionally, don't overlook the properties of prime numbers in the array. Each fraction arr/j is guaranteed to be irreducible because both the numerator and denominator are prime. This means you can skip checks for reducing fractions, simplifying your solution. Finally, watch out for off-by-one errors in binary search. Misinterpreting the bounds or mismatching the k-value with array indices can easily lead to wrong results. Always double-check how you map k to the correct fraction index and ensure consistency in your comparisons. Now, let's consider edge cases and interview-specific tips. Overlooking edge cases, such as when k equals 1 or k equals n1, can lead to incorrect results. These are scenarios where you need to select the smallest or largest fraction, so it's important to explicitly test these cases, especially for small values of k. From an interview perspective, one key insight is that the array contains sorted primes, which ensures all fractions are unique and irreducible. This significantly simplifies the problem since you don't need to worry about duplicates or reducing fractions. Interviewers typically expect you to go beyond brute force solutions and discuss efficient methods like binary search or min heaps. Be ready to explain why you chose a particular data structure and how it impacts the time complexity. For example, you might prefer a heap for its flexibility or binary search for its efficiency. Additionally, always communicate trade-offs clearly. Discussing edge cases explicitly demonstrates thoroughness, while a solid understanding of time complexity helps you stand out. Clearly articulating the components of your solution and their respective complexities is crucial in conveying your thought process. Exploring related problems can deepen your understanding of this challenge. For instance, LeetCode 378, kth smallest element in a sorted matrix, uses similar techniques such as binary search or a heap to find the kth smallest element. LeetCode 719, find kth smallest pair distance, also involves binary search combined with careful constraint handling. LeetCode 167, two input array is sorted, leverages the property of sorted arrays for efficient solutions, which is conceptually related. Lastly, LeetCode 373, find k-pairs with smallest sums, involves generating combinations and using a heap, similar to this problem. Considering alternative approaches, one of the most common is using a min heap. In this method, you push all possible fractions into a min heap, prioritizing the smallest fractions at each step. This has a time complexity of O, k asterisk log n, as you perform up to k iterations where at most n fractions are pushed or popped. However, the trade-off is that this approach can be more memory-intensive compared to binary search, especially for large arrays. Understanding these related problems and alternative strategies can help you adapt to variations in the problem during interviews. Another effective approach is binary search combined with fraction comparisons. Here, you perform binary search on the value of the fractions, determining how many fractions are smaller than a given threshold value. This approach has a time complexity of O, n asterisk log, max underscore fraction, where max underscore fraction represents the largest possible fraction value. The trade-off here is that you may need additional helper functions, such as one to count the number of fractions below a threshold efficiently. Finally, there's the brute force method, which involves generating all possible fractions and sorting them. While this method is simple to implement, it has a time complexity of O, n squared asterisk log, n squared, making it infeasible for larger inputs. The advantage is its straightforward implementation, but the computational cost is very high compared to optimized approaches. Understanding these methods, their complexities, and their trade-offs will help you choose the best solution for different scenarios and effectively communicate your reasoning in an interview setting. Great job making it to the end. To summarize, we used binary search and a two-pointer strategy to efficiently solve the problem. Remember the key takeaways about leveraging binary search and analyzing constraints. Thanks for watching, and see you in the next challenge. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!